Well, Spate have actually diversion, hydrology, all are based on water resources, and my presentation here is on understanding hydrological process in ephemeral rivers, or we could say resources for Spate. Could be not only ephemeral but also intermittent flow as well. And my name is actually Abebe Demissie, and I'm from Ethiopian chapter Spate Irrigation Network. The content of my presentation includes introduction, all about what is Spate, what is this hydrological processes, and also river divisions like intermittent, ephemeral, and perennials, and a little bit we'll say about runoff generation processes, and also factors which affects the hydrological processes or flood hydrographs, and then Spate irrigation hydrology. Also we'll see, because the core points of all the hydrological processes are data through which we could study and learn the history of what is really happening as rainfall and flood. And then we'll see how measuring data is or could happen and also should happen. And then finally the dependable flow analysis which we are using as a resource in Spate irrigation. A river basically could be divided based on how much of the year it carried flows. That is, we could say it's like perennial, divided like perennial, intermittent, and also in ephemeral rivers. And rivers, we may call it perennial if it carries measurable flow within it for most of its time. Like if it has a flow of measurable extent for more than 90% of the time, we may call it perennial rivers. And here actually the hydrograph which we can see here is a hydrograph of a flow in upper Awash of Ethiopian rivers, a river, and here we could see the flow to happen for almost 12 months of the year with some base flow, and also others could be an example. And besides the perennial, again we could divide the flow or the rivers into intermittent. That is, if the flow in the river we have is more than, is 50% of the time or less, then we could call it intermittent flow. And basically most of the flows which are starting, or flows of the first order, are intermittent flow. Rivers actually, when they start and make runoff and then time to time joining to each other, finally they will make up the bigger section of the river. And any order which starts initially and join the other one, we call it the first order, and then each first order will join and make second order, and likewise finally build up to make the main trees or the main section of the river. So all the first and second order of rivers are basically intermittent mostly. And the other type of river we have is ephemeral river. The ephemeral river flow generally occurs during and shortly after extreme precipitation or snow melt conditions, and they are very flashy, and maybe they lasts for 2 to 3 hours. And these are actually type of rivers that is based on how much or for how long they carry waters within them. Coming to runoff generation process, of course this is very familiar for all. Runoff will be generated, and runoff also is part of the water cycle. And this runoff, which happen due to precipitation, could be based on causes either infiltration exceeds or if the rainfall exceeds the rate of infiltration, or if the saturation excess happens, and therefore the core process of runoff could be generated in either of these two main reasons. Either infiltration excess, that means if the rainfall rate is more than the rate of infiltration, which basically happen in arid and semi-arid areas, and also we can call it saturation excess, which is if the soil is fully saturated, it means that the rainfall first saturates, soak all the soil, and then whatever left will be runoff. Then this is a runoff which later on become a surface runoff, and also what we have said like intermittent, perennial, or whatever, and then be resource for later use. So this runoff basically could be affected with either climate change impact could be reason, but very importantly impact of land use. Land use could affect each component of the hydrological process, like evaporation, transpiration, and also the surface runoffs. If we have green, make it fully covered, or if we left it without any cover, that is, it means that if we are not really covering the land, it means every rain, rather than being infiltrated, much of it will be turned into surface runoff, and then usually in such kind of events we'll have very sharp runoff, which is incidentally become very peak, but then that hydrograph will be flatter if the land use is changed to more green areas, or if we have more green coverage. Then in such kind of land use change, basically the short-term impact is the interception is huge, if we are planting, and then the flood generation will be also shorter, or because more of the water will be to recharge than to be runoffs. But then the long-term impact will be actually to have good recharge of groundwater, and then it means that we'll have good reserve of groundwater and also base flow in our stream, and which basically turns intermittent or whatever kind of rivers we have into perennial rivers. This impact, actually land use change impact, will affect the runoff. For example, if we take land use impacts, that is by changing pre-urban areas into very fully urban areas, then the first thing which is going to happen is those pre-urban areas, usually which have more of vegetation cover, is going to be converted into paved one, that is with less infiltration, and meanwhile it will make the peak to happen shortly. That is, it will have a very sharp rise up and also very sharp drop in hydrograph. And the other change which will happen is the peak. The peak will be more extreme than in pre-urban. That is, when we make it urban areas, then the flood will rise sharply, and also the peak will be more bigger in size than the peak we could have in pre-urban areas. Therefore, this land use change basically affects our hydrograph as well, and then the runoff also, which could be actually potential for our agriculture or for domestic or for other water uses. And besides this, there are actually different factors which affect our resources or hydrograph. Climate could affect. More intense rainfall leads to a shorter time lag, while greater total of rainfall should lead to a higher peak flow. And also soil, if our soil is impermeable or not, if it's covered or not, still it affects our hydrograph. The other is the shape of the catchment we have. If the catchment is more elongated, and if it is more or less near to the circular shape, then this elongated one will have stretched and a peak, but not more than a peak, which could be generated by a circular types, nearly circular type catchment shapes. Therefore, this is also one of the criteria to have different types of hydrograph. And then understanding our hydrology will begin not only from climate, land use, and so on, but also from the shape of the catchments we have. Then all of this, actually, the general aspect that we have talked will lead us what kind of hydrology we have in Spate systems. Then coming to the Spate hydrology, Spate's hydrology is basically, Spate itself is utilization or making use of those unpredictable, often destructive floods into benefits. And among the river types that we have talked, Spate uses ephemeral and intermittent, not the perennial one. And then, as we have talked, ephemeral and intermittent are actually which carry waters for only short period of time. And then often those resources are not measured and also will not take attention because they last for short time, and then for most of the time they are dry, and people or any planner could see those streams being dry. And for example, this is a resource actually in South Omo of Ethiopia. The flood, we could see it really carrying big trunks, but which is really dried shortly after some time, and then the planners are not really utilizing it for the same reason that it's neglected in most part of the world. And then the characteristics that we have talked for those ephemeral intermittent flow, which is to have greater variation in size and frequency, and also which they are generally generated in wadi catchment by localized storm rainfall. And also those Spate hydrology basically are characterized by extremely rapid rise in time, followed by a shortened recession. So measuring those, basically, if we are thinking as a resource, is crucial. But then while measuring, the first one is just to measure the rainfall. Of course, why we measure this rainfall and also runoff is basically the command area, if we are planning command area to irrigate, and also if we are planning ponds to construct and so on, we need to know the resource, at least the dependable resource that we could stick in. And also the classical design of those structural designs still need those measured data, and therefore measuring is very crucial. But the truth in those Spate resource areas, the catchments, the rivers are not gauged, and also we may not have good even distribution of this rain measuring device, rain gauge, and also flow measuring the measuring devices. The other reason is they are unpredictable. Those resources are unpredictable and also destructive, and measuring practically on ground is very difficult, and this all add up for data not to be available for planning and also for design in those areas. And therefore, one way or another, it have to be measured, because then we could optimally utilize the resource and also design the structures which could be safe. For example, here what we could see is Ephemeral river, still in South Omo of Ethiopia. Basically, here people stayed like for some hours, because when they crossed this it was dry, and then when return back they have to stay like for 2 hours. Just a flow runoff which lasts maybe 2 to 3 hours. And this is actually after that flows has passed, then it will be good road, the same road, which helps again for transportation. And that makes actually planners not really to think of it as a resource, because it comes and goes shortly, but it really even hinder different activities. Then rainfall measurements, actually where we have to put is basically we have to put it both in the command and also in a runoff generating area, which is in the catchments, because then we could have actually impression of really what's how the variety, how vary this resource is in both command and catchment areas. And if possible, we have to make it really cover both the catchment and the command areas in evenly as possible. And also, if possible, we have to record it in more finer resolution than possible, as much as possible, because this runoff is being formed with very short intense rainfall, and if we are keeping measuring only once a day and like only twice a day, that may not really reflect the resources, because those resources could happen even as a runoff within 3 hours or only for 2 hours, and therefore having more finer temporal data resolution is crucial. And measuring discharge still is very tough basically, but we could measure those floods even when there is flood and also after flood. How we could measure while there is flood is by, for example, floating methods, that is by putting small floats. Really, it's not necessarily be something which is prepared from factory and so on, because having no data is not really something that's appreciable, and therefore we have to measure with whatever things we could do, and then basically it's difficult to measure to do this as well practical on the fields, because if we have very wider channels, for instance, then to throw that floating things into the center still is difficult. And usually actually how they do it in Sudan, for instance, in Gash River, is one person will be from the other side of the river, and then the other person will be, then 2 people will be in the left and right side of the river, and then they throw, and then like they measure the time, how much time it takes till this float will travel like 50 meters, for instance, and then they calculate the velocity basically, and that velocity of course could be different, less slightly, or could be the same, but then they could take the average and could have impression of more or less representative data rather than to stick from which is really happening from one side. And we could use also a diver, and a diver is basically such kind of very small devices which could measure again water levels, depths. And the other is weir or flow, which we knew it's actually, which is very common still. These are actually how we could measure if there is flood. Still, if there is no flood, it's also possible to measure, for example, after flood, we can measure it, for example, using flood mark surveys, just by following where this flood left the marks. We can use still that as input for our discharge measurement. The other is slope area method, just to measure what slope in one ridge is, and then cross section again the flood mark, and still it's possible to follow such kind of things. But then still what we have measured is flow depths. Then we need to convert it into discharge, and that is what actually we need it more or less at the end. Then converting stage measurement to discharge is possible in different ways. Basically, discharge rating curve could be made for any section of a river, but the challenge is there is a sediment, and then the sediment usually changes, and not only sedimentation but also erosion changes the section of the rivers. And then how actually Sudan how they could really use, very interesting, is they measure the cross section at the beginning of the flood, and also they measure the cross section at its section at the end of again the flood, which is more or less when it's dry and really comfortable to measure. And if possible, again they will try to measure in the middle if the flow is not really so big and if it is easily possible to measure. And just say take the average of this, and already they have the velocity that they have measured with floating, and then with simple formula that we know, which is discharge to be cross-sectional area times the velocity. This is still possible, and this is actually how flow could be measured. I mean, change it into the flow depth is changed into discharges. The other is, for example, divers. This is actually in border data of Ethiopia. It's a diversion weir again, and here the diver will be put at below. I mean, at the bottom and again at the top of the measuring device. The bottom one measures the pressure of water, which is above that and atmosphere, and the top one measures the atmosphere. Then the subtracting the value which is measured by the top and the bottom diver will give us the water depths which pass with that section. And this is really interesting because we can measure even with more resolution, that is with more temporal resolution. It means with every 5-6 minutes even, and then will give us more or less good impression of what really discharge is passing even within shorter period of time. Again, to change this one, we can use different empirical equations. For instance, here in border data, the intake is sort of a broad crusted weir, and then we can use the broad crusted weir equation again to find the discharge. And of course the weir could be OG or whatever, but still we could adopt whatever formula which suits the section, and we can again convert the stage measurement into discharge. The other measuring device or possibility is through dilution. That is, we inject salts at a section, and then we measure. We will have a track variation of EC of this river somewhere downstream. Of course, what we have to make is sure is wherever we are putting or pouring this salt solution, and then downstream where we are measuring, in between there needs to be more or less a turbulence effect of this flow, and then we are sure more or less this salt is mixed with the water. And then by measuring actually at each times the concentration of salt downstream, then we keep measuring until we find constant salt measurement, salt concentration measurement, which actually assure us more or less what is really I mean, if it is constant, then it is telling us that the river is not now with added salt concentration, but it's with its own natural streams. Therefore, when it is poured slightly, the salt will be tested, and then in the middle it will be peak, and then it will decrease till we measure the river flow as it is. And that is actually sort of hydrograph which is made, and then by summing all concentration which happen, multiplying by the discharge, I mean, or the volume for the time it takes, and we can again calculate the discharge with this formula. But then measuring is also still possible unless we calibrate it, because all have some more or less some errors, like throwing a floating device and just calculating the velocity and then multiplying with the cross section. Of course it helps to get the discharge, but still we might not be sure. Then calibration some places actually could be done with current meter. With current meter, the discharge will be measured, and then it will be compared with what is really computed with methods that we have made by like floating, or it could be full through diver and so on. And then we can keep or made a relationship between these two discharges, and it will help us even if there is no current measurement, because partly we cannot use current measurement always, because it's difficult just to be inside the river and to measure the flow. The only way usually what we are making is we will measure with current method just beside, standing on the bridge. But if we need to measure discharge in the river, and wherever there is no this bridge, then what we have to make is just we have to measure shortly for short period of time this with this current method, and then we have to correlate it with whatever simple method we have, and then we can use that relationship later on. And of course still there could not be any possibility, or for whatever development we are going to any wadis, we may not have any data, so, which is with whatever method which is measured earlier time. And then we have to use empirical method like rainfall runoff modeling also, and also we have to use all local knowledge we could get from people. For example, here what we can see is the calibration after measured which is rainfall runoff modeling was conducted by NAM model, and then the runoff is the runoff which is generated with this NAM model is compared with the runoff which is measured actually in the outlets of the wadis. Then what is the purpose that really we need to analyze and so on? This discharge is mainly for designing the structures, and also to assure we are optimally use these resources. So the purpose of why we make analysis, of course, after measuring, is it could be to design structures, because those structures to be safe and to fully stand the flow which is passing across, over or under it, needs understanding of very extreme hydrology of the area, and then it helps for that purpose. The other is for drought analysis, because then what low flow or what droughts we could have in that, and then analyzing that will help us again to prepare the social, or even to understand drought could to happen in that area, and anyway to take any measurement. The other is for planning the size of command area and pond, that is just to plan spate. Still we need this analysis, but then how we could make this is also an interesting issue, because how we could really analyze to design discharge, to design structures, like to design could be diversion weir, it could be all structures that we are going to put across in the river or within the canal, needs extreme case situations, and more or less the theory is there are extreme discharge calculating mechanisms, like different hydrological analysis. Actually we do have different mechanisms of analyzing those peak discharges for which structures to be safe and to be designed for it. But for command area and pond to be planned in Spate, we don't have those methods, and also the methods that we require here is not the extreme case, because the extreme case usually we could not get them every now and then, because the extreme case we are planning is like to happen 1 in 100 years or 1 in 50 years, and therefore we came with dependable flow analysis that is to suit for planning command area and pond planning and also operations. Then the dependable flow analysis is basically, it is based on even whatever we measured, because year to year could be different. For instance, what we measure this January could be different from what we are measuring next and also after again another measurements, and therefore whatever measurement we have will lead us with different hydrograph year to year. And for planners this is very difficult because with which resource or with which hydrograph they have to stick in, and therefore dependable, I mean generating the dependable resource or a resource which more or less we could get in some probability of happening or occurrence is initial, is necessary. And that is what actually the model that we will see is doing. Then actually what the model do is it takes the measurement of, for instance, all the years for January or for February and so on, and then it analyzes the data which is measured, for instance, only for January. That is because assuming that in January of different years we could have different data, but then what we need as a planner is to have a data with which we could plan our command area and also our field structures. And the step which is adopted is actually just the step that we are adopting dependable flow analysis. First we rank in descending order, and we give it rank, and then we compute exceedance frequency, that is rank over, it could be rank over n+1, or we could have actually different options like simple formula or Hazen formula and Weibull formula and so on. Just selecting one of any of these methods, we can again find plotting position, what we call it, or what we call it exceedance frequency. And then for each months we generate flow duration curves, and then we know that for each months how much in what exceedance of frequency or what dependable a value will have. For instance, in this graph we can read that 90% of the time this value, which is 2 times 10⁴ metric cube per day discharge, will be exceeded. Likewise, then we'll have a flow duration curve which express for us the discharge which could be available always, and not always, at least in most of the time, and which could be available rarely. And therefore the planner will decide which discharge to stick in for that months. And in this way it will be a flow duration curve will be made for each months, and then finally we'll have a hydrograph for each for a year round, but based on selecting the dependable flow that we are planning to use in each month. Then how actually we can make use of the program is first we will enable the macro part, because Excel is made with macro records, and then we will actually just to enable macro is very easy. Just of course different versions have different ways. Anyhow, after making that, we'll for instance, this is the tool. Actually the tool is basically made not only for dependable flow analysis but also for storage and area optimization, but now we'll see only the dependable flow analysis. And first we need to have data actually of each month. Let me get this data, for example, which is put as exercise in this, and then after having this data we copy it first the data, and then we paste it in this section, and then just only to click this button which says dependable runoff, and the Excel automatically computes for different exceedance, probability of exceedance and that is 99%, 98%, and for all, then the planner could choose, for example, a discharge which is happening 75%, which is exceeded 75% of the time, or could be 50% of the time. And this is anyhow how this tool is working. Very simple, but it helps to compute the dependable flow analysis. And then the basically this software which we call it SSICP, will generate dependable flow like this. For example, as we can see, there is a black one with 80% of dependable dependency, and also the blue one with 50% of dependable. Then the planner will select basically which one to adopt. Preferable basically to start from to begin with more dependable flow, and then to extend the command area for more irrigation. But still, always we are doing this by accepting some risks. Whenever we have hydrograph like this, or dependable hydrographs, when we go to more higher and higher discharges to tap most of the floods, of course we are going to irrigate more or less or utilize much of the resources, but we are also accepting risks because we may not get that resources often, and therefore it is also possible to go for more or less discharges. That means more or less we are certain, that is the degree of availing that discharge is really not with much risks, but then we are underutilizing the resources. So playing with this, we have to go to really utilize the resources, maybe beginning with smaller command, and that is with with a higher dependable flow, and then going to irrigate, moving to irrigate more and more lands. That is actually accepting small risk is beneficiary. Then this is all. Thank you.